Yesterday we did solving rational equations, and I told you solving inequalities is very, very different, kind of like polynomials, but I would say this is probably even a little bit more different. Okay? So remember, with polynomials, when we solved, we just factored and picked the solutions out of the factored form when it's equal to 0. But with inequalities, we had to do the whole big sketch. We had to still do all the factoring and everything, set it equal to 0, and expand, simplify, refactor if you have to do that, and then do a sketch. So solving rational inequalities is similar to that. We don't do a full sketch, but we do something similar to it. Before we get to that, I want to ask you something. So remember this from before. When a function is positive, it's above. Remember when we did intervals of like positive intervals and negative intervals on the first day? I hope you remember that. It was on the quiz, the properties part. So when a function is positive, it's above the x-axis. In other words, y, the y values are positive. That's what we mean when we say the function is positive. When a function is negative, it's below the x-axis, the function, the actual drawing of the function, or in other words, the y values are negative. So let me ask you this question. What properties of a function allow it to change from negative to positive or vice versa, positive to negative? In other words, under what circumstances? Or in other words, what's happening at the point where it changes from one to the other? The leading coefficient will tell us a little bit about whether it's positive here or negative here, but that's not what we're asking about. We're asking about at the point where it changes, what does that look like? Very good, X-intercept. Anybody else was thinking that? Yeah, thought so. Okay, so we're just going to sketch this out. If you couldn't get it, I was going to say just draw a polynomial graph and circle the you can't see that. And circle the locations where it's changing from positive to negative. Can you do that? You should be able to do that. We want to be able to visualize this stuff. There's one there, there's one there, and there's one there. So these are, and what are those properties? They are X-intercepts. What's another one? There's actually 3, sort of, 2.5. What's another one? No? Vertical asymptotes. So think about this. Just sketch one out. It could be negative before and positive after. So it changed there. Before, to the left of the vertical asymptote, it was negative. To the right, it's positive. Take a look at this one. To the left, it's negative. To the right, it's positive. Isaac. Absolute value. That's an interesting idea, but that's like a different function. I understand what you're saying, though, but we don't have absolute values in rationals.
Is it the degree?
Like the degree will have an impact on how many times it happens and what happens, but it doesn't have to do with the actual. Oh, do you mean the order?
Like the degree? Oh, maybe. Like
the order of the x-intercept? Yeah, somebody said that this morning too. Again, that tells you what it looks like, and it tells you sort of if it's changing from one to the other. But the properties for us, for our purposes today, is still the x-intercept. That's still the thing. A hole, very good. A third one could be a hole. Now, a hole is a curious one. It doesn't come up very often. But it is possible that if I had a hole on the x-axis, I would be approaching the hole and go through the hole, and on one side of it I would be negative, and on the other side I would be positive. And a hole is tricky because if you had a hole right on the x-intercept, other things would be going on. But a hole is important, that, as you'll see later on, for another reason. So that was kind of those are kind of hard questions to answer because you're not even really sure what I'm asking. And now you understand probably, okay, now I see what he was asking. But now you're thinking, so who cares? What's the point? What in the world are we talking about anyway? Anybody feeling that way? Like what? Yes, so big deal. Well, you'll find out in a moment when we start to solve these that we need to first, the first step of this process of solving rational inequalities is identifying x-intercepts and asymptotes and holes, and then using those to break up our function into intervals and see where it's positive and where it's negative. Here's a question. I meant to ask this at the beginning and I forgot. So before we move on, I want to ask you, why can't we just solve these like we solved rational equations? How did we solve rational equations? Sometimes we did. It was yesterday, folks. Don't you remember what it was? Lucas?
I was going to say we just factor and solve for x, but
there was a bit more to it because you start with a rational expression. How did we? Nice. Multiply by a common denominator to clear the fraction. Why can't we do that here? Why can't we just multiply by a common denominator? We make things so much more easy. Let me show you what one of these looks like. Why can't we just, well, those are, well, by 0, yeah, that would sort of work, but let me try this one. Why can't we just multiply by a common denominator here? Seema? So if I changed it to equal to, you would be able to? Like that, you mean? Oh, well, yes, that's absolutely sure. But why? But why? Why? I think you're on the right track. I think you know what you're talking about, but Isaac? Why? It would be greater than x plus 2 if I multiply by x plus 2 on both sides.
Because we don't know if that value would be negative.
Why does that matter, Tyler?
Because it would change the way it would be less than or greater than.
Yep, good.
Because we have to put like -1 on the side and then we say 0.
Well, that's what we have. That's what we're gonna sort of have to do. Yes, but why? Why? It's still all. But Tyler, you're on the right track. What happens when you multiply an inequality by a negative? You got to flip the sign. Is x plus 2 negative or positive? It's both, isn't it? It can be both. It depends on the values of x. We could break this up into cases. When x plus 2 is less than 0, we do this. When x plus 2 is greater than 0, we do that, like we did with absolute value. Yeah, maybe. What about when you have two things that you're multiplying by on the bottom? It's not as easy to break it up into cases as absolute values, and there's an easier and better way for this that wouldn't have worked for absolute values. So I think you could do it by breaking up into cases the way we did, but I would not recommend it. I think there'll be too many cases. It'll be too complicated. Like I said, there's an easier way. So if you only learn one thing today, folks, I hope it's that you can't solve these the way you solved yesterday. Because every year somebody tries to, and it doesn't work. And even though we make a big deal that they're totally different, you could actually solve yesterday's questions more like we're solving today, but you can't solve today like yesterday. So please, please, please remember, whatever you do, when you leave here today, remember, when you get an inequality, you cannot just multiply by the denominator to clear it. It's like Mr. Belair had some weird thing. I'm not going to do it his hard way. I'm going to do it the easy way. The easy way is not so easy when it doesn't get you the right answer. So There's a different way that we're going to do this. And here's what it is. We are going to look for any asymptotes, X-intercepts, and holes, which isn't listed here for some reason. Probably because the holes don't really happen that often. To find any transition points, transitioning or changing from negative to positive. We're going to break this up into intervals. We're going to test the intervals. And in fact, we did this in polynomials, but we usually did it by sketching, because sketching the polynomials is easier, but some people still did the interval testing. And so that's what we're going to do. Solve each of the following inequalities. The first couple are quick and easy. And that one I'm changing a little bit. Okay, the first one is fairly quick, fairly easy, because everything's already set up for us. Would it work if this was a 1? X-intercepts don't tell me when I change from being below 1 to above 1. So that's not going to work. Vertical asymptotes don't tell me that, so that's not going to work. It only works for 0. So what are my X-intercepts? This is supposed to be the easy part. I've got an X-intercept of 3 and a vertical asymptote of X equals -2. Thank you. I hope we know how to do this. It's going to be pretty important for tomorrow. Okay, then we break this, then we draw a number line. And we go left to right. I have a vertical asymptote at -2, and watch what I do. I draw it like an asymptote. I have an X-intercept at +3, and we label them. Okay. And then I do this. Now I don't usually write out the intervals, but this is the interval x is less than -2. This is the interval -2 less than x less than 3, and this is the interval x greater than 3. So what is a number that's less than -2 that could represent this whole interval? Because what are we talking about here? We're talking about whether this function, so if I said the function f at x equals x minus 3, this is a rational function. It's a graph. Y equals this. F at x equals this. We just said the only places this will change from being negative to positive are at x-intercepts, vertical asymptotes, and holes. Does anybody believe that there's another way that that could happen? Teleportation? No, that's not functional. Anybody? No? Those are the only 3. So in this interval where x is less than -2, if it's negative, it's staying negative. If it's positive, it's staying positive. Do you agree with that? I hope so. So what's a number that could represent that interval? -10, that's the one we used before, isn't it? I like -10. You could try even -100. If I put -100 into this, the top, -100 minus 3 is negative. -100 plus 2, still negative. 2 negatives, negative on top, negative on bottom. Whatever the numbers are, we don't care. We just care if it's negative or positive. Is it below the x-axis or above the x-axis? 2 negative makes a positive. So that interval is positive. What's a good question?
Is I can't tell, is that the greater than or equal sign on the for B, is that drawn in, or is that supposed to be?
Supposed to be there. But the answer to your first question is also yes. It's drawn in and it's supposed to be there.
Okay.
Okay, the next interval, -2 to 3. What's a number that might nicely represent that one, Isaac? 0, thank you very much. And 0 minus 3 is negative. 0 plus 2 is positive. Negative over positive is negative. What's a number that could represent the interval of x equals, so a number that is bigger than 3, x is bigger than 3, could represent that interval? 100, 10, 100, pick the one you want. 100 minus 3, still positive. 100 plus 2, positive. Positive over positive is positive. Be careful of just picking out patterns that aren't reliable patterns and doing this based on that. These ones flipped back and forth. Often they do, but not always. So you can't just do the first one and then make them flip. Okay, now now what?
Please state the ranges where it's greater than 0.
So greater than 0 means above the x-axis means the y's are positive or the function is positive. So that is, isn't it, this one and this one? Those are the two intervals where this is positive. Therefore, when x is less than -2 and when x is greater than 3 are the solutions to that inequality.
Do we have to highlight it?
That's it.
Do you mean that's it? Like that's how you solve it? Yeah. These are easy ones to illustrate what we're doing. The ones that we'll actually do have a lot more algebra in them. So there's the algebra can be a little bit thick. You have to understand the testing. You have to understand why, but otherwise, it's not too bad. Shall we try another one? This one's already set up for us as well. What are the x-intercepts?
5/2.
Thank you. Positive 5/2 or 2.5. Vertical asymptote. Good. Number line. -4/3 and 5/2. So this one says less than or equal to 0. So -10 is less than 4/3, yes. I put, again, it's easy to do the math if you pick these numbers. What if I pick -100? That's -200 minus 5. It's negative. -300 plus 4, negative. So 2 negative makes positive. Zero is in this interval. Makes life easy. So that's -5/4 because the x parts go away. So that's a negative over a positive, so negative. Big positive number, 100. 200 minus 5 is positive. 300 plus 4 is positive. Positive over positive is positive. You could punch that into your calculator, by the way, if you wanted to. You don't have to do it in your head. But it's a lot faster if you can practice a bit and get used to doing it in your head. It'll also help for the sketching and everything else. Now, somebody tell me something that's different about this question that we have to take into consideration when we're interpreting our answer. There's something importantly different about this question. The fact that it says less than or equal to is what we have to be careful of. Why, though? How does it change? Max, you had your hand up. What were you going to say?
I said the asymptote, so like you can't say equal to.
So I am less than or equal to 0 here. Max, you agree with that?
Sorry?
I am less than or equal to 0 here because it's an intercept. I am not less than or equal to 0 here because I'm definitely not less than, and I'm not equal to because the function does not exist here. So if nobody ever talked about that before, it might be curious that our solution is -4/3 less than x. That's why you're all waving your hands. There's a fly flying around. Less than or equal to 5/2. Why is this one just less than and this one is equal to? Because that's an intercept and it is equal to 0 there. And this is an asymptote and the function doesn't exist there. Why did we not have to talk about this in the last question? Because it just said greater than. There's no equal to. So in that case, you don't have to worry about it. Because it wouldn't include an asymptote or 0. So we need to understand that it's different from solving equations. We need to understand that we're breaking up the interval of when the graph can change from positive to negative, using a number line, testing our intervals. We need to watch for the asymptotes. That's why we draw it as an asymptote and an intersect differently. And then we also need to understand that it's got to have a 0 on the other side. So the other part of this that's trickier is the algebra is harder than it was yesterday. Any questions before we move on to the next example? This one is still just has a 0 on the other side. Still fairly easy. So what do we have to do first? Factor everything. So go ahead and do that. Factor the top and the bottom? Yeah, because the top we need x-intercepts. X-intercepts are when the top is 0. Vertical asymptotes are when the bottom is 0. So we need the top factored for the x-intercepts and the bottom factored for the asymptotes. If you get that done, keep going and find your x-intercepts. And your vertical asymptotes. Nice. X equals -3. X equals +8. What do we do next? Number line. Is everybody okay? Remember, we want, it's got to be in order. Don't do -4, -2, -3, then 8. So we will start with -4, and it is a x-intercept. But the next one is -3. That is an asymptote. And another one, that is an x-intercept. And then another one, that's an asymptote. Like, you don't have to draw it to scale, but it would make my skin crawl if I put the 8 next to the -2. So I can't. But it doesn't have to be drawn to scale. Isaac? Faster in this case? I don't know. If you could program your calculator, possibly. But watch, it's not too bad actually. So -10. I'm going to have -10 minus 4. Now, normally I don't write this because if I'm working on paper, I can't just erase easily. But I don't know, you might want to. -10 means this will be negative, this will be negative, this will be negative, this will be negative. Do you agree? So it's positive. Now here's where it gets messy. What's the number between -4 and -3? By the way, the first two questions we used like -10, 0, and 10. But 0 is not always in, like 0 is not in this interval. It's not in that interval. It does happen to be in that interval, but it's not always in an interval. So you can't just, it's not like our rule is we use -10, 0, and 10. We use them because they were good numbers for those intervals. But you have to think about a number in the interval. What's a number between -4 and -3? There's no integers. I would do -3.5, about halfway between. Negative 3.1 would work just as well. Negative 3.9 would work just as well, whatever you want, but you got to be able to do this. So if I do that, think about this. If you want to just watch negative, here, let me do this. Negative 3.5 plus 4. Well, 4 is bigger. So this is going to be positive. Negative 3.5 plus 4, that one's going to be positive. Negative 3.5 plus 2, 2 is not big enough. So this one's still negative. Minus 8, obviously negative. Plus 3, almost, but not quite, still negative. So now I have 3 negatives. So it's negative. A number between negative 3 and negative 2, negative 2.5. So again, going back up, negative 2.5 plus 4 is positive. Negative 2.5 plus 2, still negative. Minus 8, still negative. Negative 2.5 plus 3, that one is now changing to positive. So I have 2 positives, 2 negatives. That means this interval is positive. See how they're flipping back and forth? That often happens, not always. There are some patterns that will help you cheat, but you got to make sure you understand them if you're going to take that risk and do that. Okay? You can't just assume it always starts positive and flips, because it's not true. A number between negative 2 and 8. 0 is a good one for that.
Pretty good.
Just a question. Here with this, do you mind if I give it on my format?
Yeah, of course. I don't care.
That was only 3 marks.
Oh.
And I want to talk about the second.
We'll talk about that. Yeah, okay.
Thanks.
Okay, so 0 is, yeah?
Never mind.
Oh. 0 plus 4, so that's positive. Now that one's positive. Still negative, positive. So 1 negative means this is negative. And then a big positive number is going to make positive, 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 like 10 minus 8 is now still positive. So it's all positive. Same thing, the last one doesn't always end up positive. So far it has, it seems to, but not always.
At asymptotes, do they always swap? Is the next one always off? No? Yeah.
Because we've seen graphs that do this.
Yeah, they go up toward the asymptote.
Yeah.
Actually, I haven't seen.
Then you haven't been doing the homework. Okay, so now let's read this answer. What are we looking for? We're looking for when it's greater than or equal to 0. So that's here, here, and here. We have 3 intervals, and watch for where it's equal to and where it's not. So negative 4 is an X-intercept. So x less than or equal to negative 4. This interval is between negative 3 and negative 2, not equal to the asymptote. It is equal to the intercept. And the last one, greater than 8, but not equal to because it's an asymptote. All right, we still got a few more to do here. This one's going to be fast. How'd you figure that out? Factor. Do people already start factoring? Good. So we have a whole. So I'm going to, and then I have an x-intercept of -4 and a whole at +4. No vertical asymptotes because the x minus 4 is gone. Now, when you do the testing, you can just punch it into the x plus 4 because the rest of it is going to cancel anyway. Like if it's negative here, it's going to be negative there, and that's going to make, you know what I mean? Like these two are going to be the same no matter what. Or you can punch it into all three, whatever you want. So to the left of -4, -10, -10 plus 4, still negative. I can only imagine if somebody didn't fully understand what I was doing here and how I was coming up with these negatives and positives, like if they weren't following that, it would seem like magic. Like I am so lost. He keeps saying these things and pointing to something and saying negative, and I don't know what's going on. If you feel that way, like talk to me about it after. I mean, you can ask now, but if you don't want to, like talk to me about it after, and I'll explain it more deeply because it's important that you understand. Or you can use a calculator, but it's not that hard. I just worry that if anybody feels super lost right now. Okay, but we're good. That's negative. Next one, I could use 0. I could use positive. Oh, I'll use, sorry, it's between here. So I'll use 0 between -4 and 4. So 0 plus 4 is positive. And then if I use a big number like 10, 10 plus 4 is still positive. So still positive. So it doesn't always flip back and forth, as we can see. In fact, at wholes, it often wouldn't, I think. However, there's still something else we have to think about. What's my solution here? Oh, that's up, done? So -4 is less than or equal to x less than, what did you say? Less than 4, and x greater than 4. So our solution has to split that up because, again, the function does not exist at the whole. Well, I suppose, yeah. It's similar to an asymptote. Function doesn't exist there. We still have to do the testing, except often at asymptotes it will change and often at wholes it won't. But yeah. Okay. Doesn't look too different. Looks almost the same as the other ones because they just had a 0 and this one just has a 1. But we can't, like there are no x-intercepts or asymptotes here. They won't help me understand when this graph is above 1 or below 1. There's no way to do that. So what am I going to do? Move the 1 over. Good idea. -1 greater than 0. What do we know about this function? Do we know where this function has x-intercepts and asymptotes? Don't tell me it's there, because it's not.
Is that -1?
We got to put all of this together in one fraction, and that's what makes this stuff tricky. That's why the algebra is a lot thicker in this one. So I got to get a common denominator. And watch this. Put your pencil down and watch, because something happens here. X plus 3. This is what people do, minus x plus 2. If you do this on a test, it's a grade 9 mistake. It's so small, but you're going to turn something that's factorable into something that has no solutions. And then all of a sudden, you can't do the rest of the work, and you're going to lose all kinds of marks. What did I miss? This has to have brackets because I'm subtracting the whole thing. And that makes a big difference, just that little, and then I have to distribute the negative through. So this is x plus 3 minus x minus 2. X minus x is gone. 3 minus 2 is 1. And this one ends up being super easy because it's got a vertical asymptote at -2. And I just test the one side, test the other side. I don't think we need to see this. It has one solution. Like it's negative there and positive there. So when x is greater than -2 would be our solution. But that part is all the same as before once you get it into this form. What's wrong, Seema? Are you sure?
It's alright. How many steps do you want us to show?
Let's do another couple of trickier ones and then you'll probably see. You probably know that I like to show extra algebra the first couple of times we do this stuff, just so it's written down. So if anybody ever looked at this after the fact, they could follow the steps more clearly. But it would be the same kind of thing that we usually show. What do I have to do here? Move the 1 over. Common denominator. So watch, I'm going to go 2x squared minus x minus 1 over x squared plus, and we're going to have to factor. Do we need to factor yet? Not really. So I moved the 1 over and turned it into the denominator over itself, so it's still 1, but I have a common denominator. Should I have factored the top? I could have factored the bottom if I wanted to, because we're going to have to eventually anyway, and it's not going to change. I don't think there's any reason to factor the top yet. We just have to re-expand it to collect like terms, right? Watch. So this is going to be 2x squared minus x minus 1 minus bracket x squared plus 3x minus 18 all over x squared plus 3x minus 18. Right? Why would I factor this? I don't think it's factorable anyway, really, but maybe it is. But why would I factor that if I'm just expanding to collect like terms anyway? Remember the rational expressions practice we did at the very beginning? This is where this really comes into play. What's worth your time doing? All right, so 2x squared minus x squared is x squared. Negative x minus 3x is minus 4x. Negative 1 minus negative 18 is negative 1. Plus 18, which is plus 17. What do I need to do with the top? Factor it. Is it factorable? 17 is a prime. So 17 and 1. I don't think that's going to add to 4. So then what do I do? That doesn't mean it doesn't have x-intercepts. Quadratic formula to find the x-intercepts. Yes, that's what you would have to do, which would be a pain. Don't worry, we're not really going to make you do that very often. But yeah, you could do that. Does anybody know anything else about this, though? Anybody check b squared minus 4ac? Somebody check that quickly. Negative. So b squared minus 4ac is less than 0. Therefore, no real roots. And what does that mean? No solution. That's not really what we're doing. We're not solving it. Thank you. Very good. No X-intercepts. So I have a vertical asymptote at x equals -6 and x equals 3. -6, 3. It works out to positive, negative, positive. And I get my solutions. When is this greater than 0? Therefore, x less than -6, and x greater than 3, because it's just greater than. Yeah?
Why isn't the 3 drawn as an asymptote?
Oh, good question. I don't know. Thank you. We're going to do one more. This one's already got 0 on the other side. This is a good one. Something interesting happens here. Yes? If you think this has no x-intercepts because of the 1 and the 2, and it has a vertical asymptote at x equals -2 and x equals 3, oh dear, nope. We cannot read any properties from this graph because it's this minus this. It's a totally different situation. It is not the same as the stuff we've been doing. It's not in the right form. So what do we have to do? Same as before, common denominator, but this time instead of a 1, I've got more fractional stuff. Okay, so watch what happens. We get 1 times x minus 3, over x plus 2 times x minus 3 minus 2 times x plus 2 over x minus 3 times x plus 2. So this is x minus 3 minus 2 bracket x plus 2. Is that okay? So x minus 2x is -x. And -3 minus 4 is -7. Now this is where it gets interesting. There are several subtly different ways that you could solve this question. And it's entirely up to you which direction you go. We're going to do it a couple of different ways and see a couple of the differences. Like you could go ahead and solve it right here, not go any further. But what might you do? Yeah, would that be useful? I don't know, it's up to you. I would tend to think a lot of people would prefer it like this. Why? Because it's easier to see that -7 is the x-intercept here than it is there. Some people would probably say 7, and that's wrong. -7 minus 7 is not 0. But it's pretty easy to see that -7 is the x-intercept there. So I think that's a good idea. But there's still two different ways that we could solve this. And like I said, we're going to do both. What could we do next? What do we have to do when we multiply both sides by -1? Flip the sign. So we're going to do that over here. And then over here, we're going to do the other way. So if I flip the sign, I get x plus 7 over x plus 2, x minus 3, greater than or equal to 0. And over here, I'm going to pull the negative out front. I get x plus 7 over x plus 2, x minus 3. One or the other? My x-intercept, I'm going to do it in the middle because it's the same for both. It's -7. And my vertical asymptotes are x equals -2 and x equals +3. So I've got an intercept at -7, an asymptote at -2, and an intercept at 3, and same thing over here. Yeah. Oh, thank you. Okay, put your pencil down and watch. Number that represents this interval, -10. -10 plus 7 is negative, so 1. -10 plus 2 is negative, so 2. -10 minus 3, negative, so 3, 4. So that's positive. But over here, 1 negative, 2 negatives, 3 negatives, that's negative. So that's different, but some of you are already noticing it better be different because this says less than 0 and that says greater than 0. So it's going to work out, you're going to get the same answer. Next one, I'll pick -4. Positive, negative, negative, and then negative. So I've got 3. On the other one, I've got positive, negative, negative. So 2 negatives, so that's positive. When I do 0, I get positive, positive, negative, negative. So this one's positive, this one's negative. And then sure enough, the next one, I've got, let's say 10. So positive, 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 negative. So see what I mean? It doesn't always end with a positive. And I have positive, positive, positive. So this one is positive. And watch. Where are the intervals where this is less than 0? Here and here. And where are the intervals where this is greater than 0? Same intervals. So your solution, and this was including, so is -7 less than or equal to x less than -2 and x greater than 3. In both cases, same solution, subtle differences, but things that you have to pay attention to and understand and decide how you want to do it, what's best for you.